the information about the class wasn't. I was wavering whether to have it or not because of the um, amount of activities for today. But we move. All right, let me open my slide and we kick off real quick. Just a second. So again, we probably will just do about an hour, right? I don't want to cancel it entirely, so I thought, um, okay. Yeah, window. Okay. All right. It's a share. All right. Okay. So last week we stopped at we only got to slide 6. You know, I'll quickly run through this and see if we can start the scenarios. There are 3 scenarios just for session 1. We're supposed to run session 1 for just 1 week, and we are only a third of the slides. We've only done a third of the slides. So, okay, I think we spoke about this last week, talking about what makes a PLC different from the PC. Fundamentally, the 2 devices use technically the same computing infrastructure. It is the way they are built that is different. A PC, is a personal computer, which, I mean, your laptops, your desktop, and all those other things, they use microcontroller and microprocessors. The same thing the PLC uses, right? Everything. And so that is the characteristics of the general PC. And this is the characteristics of the industrial PLC. The key word there is it is industrial, number 1. The second thing is that most of the time it is rail mounted. And then the most important thing here is it has a defined safe state output. BSOD, who knows the meaning of BSOD? BSOD, I think it's the blue screen of death. I'm sure that many of you would have encountered it. That's very, that blue screen, when the computer crashes, it just stops everything you're doing. We cannot allow that to happen in the industry. So that is why we have a defined state, safe state output. And these are the characteristics. Determinism. That is what makes a PLC different from a PC. Defined fail states, cyclic execution. In the group during the week, we're discussing, and we're discussing what makes a PLC different and PLC programming and software, right? I can tell you for a fact that you can run on some PLCs today, you can run Python scripts on them. Of course, all the ladder logic and everything, if you go to the back end, it is C++ and embedded C that is running, right? So both of them use the same programming infrastructure, right? But determinism, defined fail states, those are the things that stood PLCs as apart. So discrete inputs and analog inputs. Discrete takes ones and zeros. Analog takes a range between 0 and 100%. All right. So you can scale this 4 to 20 milliamp between 0 and 100%, where 4 will be 0, what we call the live 0, and 20 will be the 100%. The same thing to 0 to 10 volts, which is common in HVAC and lighter applications. RTD and thermocouple via resistance or millivolt signal. Then pressure transmitters, gauge, absolute differential, flow transmitters, electromagnetic, vortex, Coriolis, level transmitters, radar, ultrasonic, hydrostatic. All right. PLCs also have relay outputs, which is volt-free contacts. They just switch any voltage. They are slow, 10 millisecond. 10 millisecond. We know how slow 1 second is. We know how fast 1 second is. So you can imagine 10 millisecond. 1 second is, how do you convert a second to millisecond? Milli. You divide a second by 1,000 and 10 of those, right? So 10 millisecond. We still regard it as slow in the PLC environment. You have the track outputs, which is used for AC loads only. And they are solid state, no moving parts, and they are used for heaters and lighting. We have transistor outputs, which are DC only and fast switching, less than 1 millisecond. That's actually a second divided by 1,000. And it's used for high-speed counting, servo drives, PWM signals. And then you have your analog output, 4 to 20 or 0 to 10, controls, VFDs, control valves, and positioners. All right, so if you begin to peep into the industry, right, where you have conveyor belts, on that conveyor line, you have product passing through, and you have maybe passing through at high speed and high volume. You can be sure that somewhere, a transistor output of a PLC is being deployed, because on conveyor lines, it's most likely you'll find a proximity switch, inductive switch, and all of these different switches, right, for counting. Okay. Okay, so the scan cycle, we discussed it. Yeah, so the scan cycle is actually important. So I'll use the platform to explain that shortly. Okay, so implications of the scan cycle for logic design. Input snapshot is frozen for the scan. Once during a scan, let's say the scan cycle for that PLC is 30 or 40 millisecond. If 10 millisecond was assigned to the input scan. Immediately after that 10 millisecond, every subsequent input between 11 and 30 millisecond and the next 30 millisecond, sorry, between 11 and 40 millisecond, that input will be ignored, right? And the implication is that if that input is important, maybe to product quality or to safety, then you need to find a way in your program to you need to find a way in your program to account for it, because we were saying that 10 milliseconds is slow. You can imagine ignoring an input for up to 30 milliseconds. So your process requirements will determine that. And like I've always said, these are the considerations, these are the thinking that separates the boys from the men. These are design thinking when you factor in all the necessary conditions. So the logic order is execution order. Wrongs are evaluated top to bottom, and then the wrong that sets an internal bit will make that bit available to all wrongs below it in the same scan. The same bit used by a wrong above is not updated until the next scan. So we always need to think about the gap between this scan, going through this process, going through the inputs and the time to go through it again, right? So output writes are deferred. You can write to the same output coil multiple times in one scan. Only the last write takes effect at the right output phase. So avoid duplicate coils. It is a programming error, not a feature. If you don't know what a coil is, we'll look at it in the scenario, right? One-shot instructions are scan aware. Rising edge and falling edge contacts produce a one scan pulse. Using them in subroutine call multiple times per scan can produce unexpected results. You need to understand the execution context, right? This is very important. Excuse me. You need to understand the execution context. I will suggest that you take note of this rising edge and falling edge contact and just go have a look at it so that you'll be able to if you're not familiar with it again, so that you'll be able to understand. This is very important, right? The rising edge and falling edge, they are one-shot instructions, but they are scan aware, right? So because if you use them in multiple subroutines, they might change at any time, right? And you have tied this rising edge to a particular tag, and you are using that tag in multiple locations. After using it in subroutine 1, subroutine 2, probably you are still going to use it in subroutine 3, 4, 5. If it now changes, you get an unexpected result, and that is not determinism. The mindset we use to approach PLC operations or PLC programming is determinism. We need to know what will happen, even in the future, up to the point that if this PLC fails at all, how will it fail? We need to have that clarity. Okay. So mode architecture. We have the manual, the automatic, and the maintenance. Excuse me. We have the manual, the automatic, and the maintenance mode, right? And this is key. You can operate your PLC in manual mode. Each output is controlled individually by an operator. It is used during commissioning, during maintenance, and during fault investigation. That is where you do. So, okay, I was in a class yesterday and I was demonstrating how you force inputs or you force outputs, right? So we use a lot of forcing in that instance, right? So the PLC executes commands, manual commands without sequence or interlock checking, but with output limits. Automatic mode, the PLC runs the full sequence logic. Outputs change only when program conditions are met. The operator commands the sequence start-stop are not individual outputs. And then maintenance mode, a restricted subset of manual, typically a single device at a time, at reduced speed or partial stroke, used when physical access is required, usually requires a key switch. So you have that key to switch on your computer, on your PLC to switch from any of these modes, right? So the skill catalyst simulator, there's a scenario motor start stop with manual auto mode switch. So complete after this session. So the transition interlock requirements, if you are moving from manual to automatic, there are interlock requirements. All permissive conditions met. The pressure, the levels, the temperatures, everything must be in range. There must be no active faults or alarms. All equipment confirmed in correct position for auto start. Emergency stops, e-stops, LD, and then process variable within acceptable initialization window. These are the conditions for you to move the PLC from manual to automatic. And then if you are moving from automatic to manual, you must freeze or ramp output to a defined state, defined intermediate state, no step change in process variable, and then log the mode change with timestamp and operator ID. So as you are changing the mode, you are changing the mode, your ID is going to be logged that you are the one that did the changing, that you moved from automatic to manual. And then you need to provide the reasons and all of those things. So you can see the defined, right? Emphasis is on defined because we need to know what is happening per time. So PLC programming is not software development. A PLC logic error can injure people or destroy equipment. A software bug just causes an incorrect result. I mean, oftentimes they just send you patch. You just connect to the internet and update your Windows, boom. You can remove bug on your Windows system, or, oh, this thing is not working. Okay, let me look into it. You open the code and you troubleshoot, and then you fix it. And everybody is okay. But for PLCs, it's not as straightforward because the implication of a logic error can injure people. It can damage equipment. It can even destroy products. Imagine in a brewing process, in a brewing process, for example, there is a point where you leave the process to ferment, and you leave it for X number of hours to ferment. I'm forgetting this, and I've automated a brewery process before. So you leave the product to ferment for X number of hours. Now imagine a logic error that initiates eating during the fermentation. If you have a batch of let's say beer or alcohol you are producing, and then it's in a fermentation window where you have to strictly monitor I think the density, the temperature, and all of those things, and you need to keep them within a range. But then a logic error, probably a timed logic error or something, or a dynamic error somewhere, just initiated eating of that process. What you realize is that you have destroyed that batch because you have interrupted the fermentation process. Right. So logic error, software bug, and logic error. You can see motor runs when it must be stopped. Valve opens into high pressure line. And when we look at motor, we should not be looking at it as all these are 2 kilowatts motors. I was in a cement plant somewhere in the north some time ago, and I saw a motor. I mean, I stood beside the motor. The motor was almost as tall as I am. I mean, in height. So you can imagine not controlling such a motor in a defined order, right? So valve can open into high pressure line, process continues in unsafe state, equipment damage or process loss. It may not manifest until commissioning. I mean, a logic error, and it may require plant shutdown to correct. One of the things plant managers does not want to hear is unplanned shutdown. They don't want to hear it because it costs them money. They lose a lot of money, you know. So the 7 questions that you need to have in mind. And yeah, I think you have this slide. It's important when you begin to work on your scenarios, right? It's important you go. I mean, the scenario is not a lot of codes, but begin to practice begin to practice developing your program in a professional manner, right? So document this. This should be part of your toolkit, right? Document it. Answer this question before you even begin to code. What is this process producing, and what does success look like? So that is what defines the control objective and the acceptance criteria. What are the inputs, the sensors, the switches, the operator commands? And these sensors, you know the sensor, let's say proximity sensor, MPN, PNP, all those configured, NC, NO, and all of those things. And you get the data sheets and you keep it in a folder on your computer. The same thing with the switches, and then you have an Excel sheet of the operator commands. So this determines I/O module spec. So it helps you to determine what I/O module you are going to use and the kind of signal conditioning requirements. Then the third one is, what are the outputs? Your actuators, your drives, your indicators. Again, it helps you to determine the output module spec and wiring topology, as well as how you're going to organize your logic, your rungs, your instructions, and all of those things. What is the normal operating sequence? You need to define that step by step. So it defines the sequential function charts or state machine structure. And then what condition must be true before any action is permitted. This defines every permissive and interlock in the program. Even if you are not developing a program from scratch, you need to have this understanding because you will need to maintain programs written by others. And somehow, these questions have been answered before that person wrote that program. So these questions will help you to put yourself in the mind of that programmer so that you can easily find whatever you are going to find in that PLC. So what can go wrong and what must the system do in each case? This defines alarm philosophy, your false responses, and safe states. So you can look at this now. So we have our alarm philosophy, number one. There is an ISA standard that backs that. And then there is a fault response, even faults that we don't even know. We want to be sure that we have a response, a fitting and suitable responses for it. And then we define safe states. All of this, you'll be able to do this if you understand this. This is essentially understanding the process. And then what does the operator need to see? Command and override. So even whatever the operator gets to override in the process, you as the engineer, you permitted it. So the operator will think that, oh, I'm just doing my thing, I can override that. But you have in your system design, you have determined that this override is safe within the context of questions 1 to 6. Because you have analyzed what can go wrong and what must the system do in each case. So within this override window, you know that everything is okay. And this defines the HMI, the operator interface, and the access level design. So let me quickly run through this. This 14, I think we have 17 slides. So this is the live exercise. I'll show you where it is. So log into the Skill Catalyst. If you don't have an account, you need to go create one. You open the simulator, you complete the IO table, you identify and classify all inputs and outputs. You use the structure table in the activity, device, signal type, PLC address, and function. You define the control objective, you map safe and unsafe condition, you configure motor start/stop in the simulator. So look at this. In a 6-step procedure, it's only in step 6 that we started writing the program. Right? It's only in step 6 that we started writing the program. And this shows the emphasis that engineers take when planning a system or when planning the automation of a system. So the scenario 1. So S1, SO1, I will show you when I get into the platform, right? It is the motor start stop. It is discrete control. So you have to build a motor start stop circuit from a blank canvas. 7 rungs, ceiling contact, normally closed stop, e-stop, overload interlocks, run feedback timeouts, time on delay, 3 seconds, OTL, OTU, fault latching, and fault reset. So 11 tags, 9 auto-checked objectives. So this is, I mean, if you're really serious about this, you should just go in there and get this done within the next 1 week. Because, okay, for starters, the platform is going to be gated for payment by the end of this week, right? So by the end of this week, it's going to be gated for payments. Because S102 and S103 are advanced, they are actually behind the payment gateway. I've been looking at how to bubble this one, whether there is payment or not, you'll be able to complete this. I've been looking at how to bubble this up so that it will be outside the payment gateway, so that we won't interrupt this progress, right? But the point I'm making here is this is a real training exercise. In fact, this is what many people will offer you as paid training, and you spend days in class, and this will be your hands-on practical. So you have a structured you have an opportunity. It's saying we estimate 10 minutes, 20 minutes, but it's based on your experience, right? So you have the opportunity to go through this discipline. Honestly, if you go through this discipline, it's going to move your PLC knowledge, right, from 0 probably to about 20%, because you'll be covering a set of instructions that are commonly used in many PLC programs, ranging from simple to advanced. The S102 manual and automatic mode, the control philosophy in practice. So it just extends S101. It will be preloaded with a working motor circuit, add a real analog tank level input, 0 to 100%. So these are additional instructions, right, for comparison contacts for low 20% and high 80% thresholds. Automatic motor start stop based on level, inlet valve, and mode in EBIT on the manual start run. Then S103, full pump station, which will be like a mini capstone for this session 1. Next week, we'll go into session 2, right? Blank canvas. Now, we are talking about 25 tags, full automatic sequence, valve before motor with feedback confirmation, level control 20 to 80%, II alarm at 90%, 3 timeout fault parts, e-stop immediate shutdown, 9 auto-checked criteria, self-assessment checklist at completion, right? And this is what this teaches you. Discrete logic fundamentals. The first one that we are supposed to do is ceiling contact, the NC philosophy, OTL, OTU latching, and all of these compound reset conditions. The safety principle that a fault cannot be reset while the motor is running. You really need to experience this. And then the second one will teach you architecture and analog, mode architecture and analog signal, the relationship between manual and auto, and then the addition of these instructions, right? And then S103 will teach you integration and engineering judgments, right? So sequence starts up with feedback gates and So you see that this is very loaded, and like I've always said, if you jump on something and you can do it within a few minutes, I mean, that's probably something you know. But learning takes place when you attempt to acquire knowledge and you face a very strong obstacle. And then that obstacle will now make you to realize that, ooh, I thought I knew this. I don't, I, I mean, in this instance, I don't know Jack. So your ignorance will be defined at that point, and you know what to do to conquer that ignorance. And if you now do that thing, you take the action, you take the step, and you chip away at that block of unknown, then you realize that, okay, the more you go into it, the easier it becomes. And then within a short time, you master it and you tuck that in under your belt, and it becomes part of your experience or part of your knowledge. And then you'll be waiting for the opportunity to use it. Is anybody hearing me? Give me a thumbs up if I'm still audible. Okay. All right. Thank you. So, key points to carry forward. The PLC's value is determinism. That cannot be overemphasized. It is not speed. It is determinism. We can know what is happening per time. Every output updates in a defined time window. Every scan, without exception. Timing is very, very key. Even in embedded system, at some point, we consider timing. I mean, at the level of you're using Arduino and stuff, yeah, you do it, and you can afford 1-2 millisecond delay in some instruction execution. But at some level, we need to consider timing. So you know your signal types before touching the IDE: discrete versus analog, active versus passive. Wrong module selection cannot be fixed in software. The scan circle is not a detail. It determines whether logic executes in the order you intended. One shot, duplicate coils, and scan relative timing issues are all scan cycle problems. Manual, automatic, and maintenance modes are not just a selector switch. They are a safety architecture. Every transition needs explicit interlock conditions. No programmer writes good control logic without first answering the 7 questions. So if you don't know that 7 questions, you can safely conclude that you are not a good programmer, right? The control objective, the IO list, sequence definition, interlock list, and fault responses come before the ladder. And some people can get away without knowing the question, but really, and with due respect, if we have technicians here, I mean, I work with technicians a lot. The requirements of training standard of the engineer is different from the requirements of the training standard for the technicians. So we can accept and allow some things from technicians, but we cannot from the engineer, because we are the system creator. So if I sit on an interview asking you some questions and whatever, even if it's an engineering role that you are interviewing for, I know in my head that you cannot function in that role, because it comes with very heavy responsibility. I'm not looking for someone that understands XIO, XIC, and all of those things. I'm looking for someone that can think systematically, 360 degrees thinking. Someone that can anticipate, someone that gathers data before even making any programming decision. And it's a good strategy in interviews when someone asks you, how do you solve a programming problem? If your first action is to start writing XIO, XIC, and XI whatever, it's a flag already. And you realize this thing, except you have been specifically instructed that go straight to the program, right? the ideal thing is, even if they give you the control philosophy, the competent engineer will want the user, the system owner, to tell him in his own words what the system is supposed to do. So you've given me a document, I've read it, this is a control philosophy. Based on that document, I'm going to ask you some questions to make some clarifications. Right. So, yeah, the skill catalyst simulator is where these concepts become physical. The motor starts, the wrong you write today, pa, 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 and all of those things. So, yeah. So this essentially selling the skill catalyst to you. I mean, I am personally very proud of it. Um, I'm proud of the work the team has done in putting this together. It's very, very comprehensive. If you have an idea of the amount of documents that we had to read, analysis, arguments, and all of these things, it's mind-blowing. Right. So we'll just quickly make that demonstration and, you know, yeah, let me share screen. Get to know the training from post made after the training session that I had on. Well, so the group is open to all. The someone will drop it's a WhatsApp group, so it's open to everyone. Someone will reach out to you so we can it will help to plan a call. All right, can you please help action that? Yeah, let me 1 second. Second. I want to share my screen. We'll quickly do this for 10 minutes. I'll just provide the guidance and then uh, so, all right. Okay. Um, all right. Can you please help me? Okay, so I'll probably just get into that group and then um, get into that group and drop a message. I'll respond to it after my. Cool. All right, so that's the simulator, and it will take you through all the process. So it's in beta testing in 7 days. This should end. So a lot of changes are still coming, especially in the look and feel. All right. So we go into this. Let me go back here. So you can go from here and go directly into the simulator, actually. So it takes you into the simulator and then you have the scenarios. But let me just walk you through. So from here, I think you log in. I mean, I am already logged in, right? So if I go to my dashboard, these are the courses I've started, I've been working on. All right. I am professional because I'm a paid user. I mean, the non-paid users are learners, right? And I'll quickly walk you through the features of the platform. So you have the list of the courses that has been fully concluded here, right? So these are electronics and embedded system based. This is process control. In this process control, this particular course is an academic level course, right? And let me open that. It's a very, it has all the necessary mathematics rigor. It's control system now presented in with the academic mindset, right? So on the platform, you can approach it from the academic side. You can approach it from the industry side where we hide all the mathematics. So here you talk about your transfer functions, your Laplace, and all of those things. So it's just with one of these that's developed and it's still ongoing. These are the available simulators as of today. We'll be using the PLC simulator, the VFD, and stuff. But let me quickly, this one, they just worked on it yesterday. I've not tested it myself. This is a sandbox where you can create a process from scratch. And the feature is such that, so for example, you take a two-phase separator, or okay, so those are the things that needs to be tested. You take a two-phase separator, you take a PID controller, you connect, you do the connection, you take a generic sensor, you do the connection. Okay, so you do the connection and you can, all the parameters of each of these sensors, you can set it here, right, for your PID. You can see all your PID parameters. They are there. The characteristics of this two-phase sensor, two-phase separator. A two-phase separator is used for separating components of crude oil into whether water, oil, or gas, you know. So bottom line here, you can create a process, run it, save it. You can save it in the cloud. You have your project. So this is a test project I created yesterday night to test it, and then you have templates from which you can start. And we've started moving into advanced topics such as industrial communication, Modbus, data acquisition, VFD fan control, and so on and so forth. I've not opened all of these things. So yeah. So that's the simulator. So let's go to the PLC simulator, which is our business for today. All right. This is a simulator, and excuse me. This is a simulator. I mean, if you use this platform last week, you realize that we have changed, we have moved things around a bit, and it's a bit more user friendly. Engineers do design things to they make life difficult. So now we have three tabs here. You have the ladder logic. There's a logic tab. We have the process view, which essentially we're going to change this name. This is a panel, your control panel, because this is where your start button, stop button, overload, motor, and whatever is. And then you have your process diagram here, right? So once you have your scenario, the first thing you do is you run your program. As you run the program, you can see the scan and all of those things. And then you can come here. We're working on the video tutorial. Video tutorial, but we are still working on it. But there's a user guide. There's a user guide. So you come here and you click on start. So the motor is running. right? And the status is run. So if you go to the process view, you can see on the panel that the motor is running, and this is the overload. This is the stop push button. So if you click on the stop, it stops. If you click on start, and then if you go to the ladder logic view, you can see that the rungs are green, right? And this is the watch table, right? You have 3 inputs, 2 outputs, 1 memory. And you can force input or output. So the overload fault is presently false, right? This is presently false. So let's see what happens if I force this to true, this value. If I force it to true, right, you can see that the overload indicator comes on, which shows that there is a trip, right? There is a trip. So if you go to your process diagram, you can see your motor has stopped, right? So essentially, we just took the physical manifestations of all these things in the plant. We just presented it, on software. We wrote all the physics engine, all the parameters and everything, all the limits and everything. And we represented it with, they are behind this. And this is a guide, actually, right? It tells you a bit about the scenario. It tells you a bit about the scenario, right? Tells you about your common mistakes and the things you need to, the aha moments, right? All the contacts, all the instructions you use there. And then you have all the instructions explained here, right? Example, XIC, passes when start PB equals to true, and so on and so forth. And then you have your help also, right? You have all of that there. And here we have, okay, so I need to stop, right? You can edit this scenario. So if you go to edit program, you can change this instruction. These are the instruction. You can change this to equal to, right? Or not equal to, less than, and all of those. So you can change the instruction and then you commit, right? And then so you can run programs logic as you want it. It won't work. If it doesn't work, you try again, break it, make it, and all of those things. So you have freedom to learn. So on the scenarios, okay, I need to discard. So on the scenario, you open, so we have about 20 something scenarios presently. There are still over 40 scenarios planned for the platform. And these scenarios are exact scenarios you will find in the industry, right? So they are not just arbitrary generated scenario. Like this motor stop with ceiling that we're talking about, there is hardly any factory or industry that you won't find this block of code in there, right? So to the program, we have our S1. So this is, you want to get into the PLC simulator, you click on S1, which is, so you have a blank canvas. It's an empty program, S101 motor discrete. So you use edit program to start building, right? So you come here and then you add a rung, and then you add your instruction, XIC, you select your tag. So the only thing that might be, that might look like a restriction here is that for every scenario, all the tags have been created, right? So every scenario has its tag database. You cannot create another one and you cannot rename it, right? To create a new tag, a new scenario for yourself, it's another scope that we are working on to add to this, right? And we are trying to link the sandbox and this so that you can write your logic here and then use it to run the process you've created on the sandbox. That will take a bit of a while. I mean, a while to. We are working on it. It's in the pipeline, right? So you select your tag, right? Say XIC, and then you apply, right? And then you come to the output, and then you select your motor, right? You select your tag, let's say motor coil, right? And then whether it's output energized or large or unlarge or whatever. Let's say this, and then you apply. So your rung is created. Then you can always add rung, add rung, add rung, and do all of those things. So you have the instruction, right? Go walk through it. Go walk through it. On the platform here, we have a community where we have discussions, right? So I'm going to create a discussion for this series. I'll create a topic for it. So if you run into any problem, you can present it here and people will contribute to it. As well as on the WhatsApp group, you can drop your challenges there, screenshots and everything. And then people will make suggestions, the good, the bad, and the ugly suggestions. But overall, we'll all learn together. So I guess I'll stop at this point and say thank you for your time and for listening. So I'll just take questions for 6 minutes so that we can shut down by exactly 8:15. I have a very long day. I have about 3 other lectures planned for today. Yeah, thank you. So we'll continue again next week. We'll start with session 2. So we've dealt with PLC session 1. We'll start with session 2 and confirm that you have the slides. How can you add more instructions? Okay, so for now, like I said, the simulator is scenario based, right? We prioritized, at least let's get familiar with the existing industry processes, the common ones, right? Very soon we'll be able to create entirely new program because it will be needed in the sandbox that I showed you earlier. Right. And for those interested, there is a leaderboard. This is designed to encourage daily learning, right? It's designed to encourage daily learning, where we rank people based on the time spent on the platform to learn, the scores they've gotten from the platform, and then so we have competition also. So this is the global. This is weekly sprints, right? So these are the guys that this week, if you're in a cohort, right, the ranking will be here, and then for the competition. So competition is a monthly competition. It runs every 30 days. And at the end of the month, eventually it's going to, you begin to assign, awards and all of those things. One of the features of this competition is we want to stimulate an inter-university competition where, we rank each university based on the temperature of knowledge, Yeah. So I'm just saying this because of questions. So any question you tell me. Well, if there are no questions, okay. How can you add more? Okay. Good morning. We just joined the WhatsApp group yesterday, so we don't have a just ask. Um, just ask. Someone will drop the question. I mean, sorry, someone will drop the just ask on the group. Someone will drop the slides and the recording link there. I mean, it's a community of almost 700 persons. There are almost 700 persons in that WhatsApp group, and it's growing. So just ask, someone will respond. Okay. Seems we don't have any question. I'll say thank you very much to everyone, and I wish you a beautiful weekend. And then we'll continue again next Saturday.